So let's practice our skills now and our knowledge from the previous video with regards to the Bohr model of the atom. Let's use that knowledge and these two equations to answer this question, to calculate the wavelength associated with a transition of an electron in the Bohr model of the atom. Specifically, we want to know the wavelength absorbed when an electron moves from n equals 2, so that means an orbit of 2, to an orbit of 6, not shown on this picture here, but further away from the nucleus. So we need to calculate the wavelength of radiation absorbed, so we know that our energy is going to be positive. That's going to take energy to do that. Calculate the wavelength of radiation absorbed when an electron moves from an orbit of 2 to an orbit of 6. So my initial orbit is 2 and my final orbit is 6. And knowing that is important so we can plug in the appropriate values of n for the equation that's shown here. We need to calculate that change in energy first before we can calculate the wavelength using Planck's constant and the speed of light. So the first thing we're going to do is calculate the energy associated with that transition, and we will do that using this second equation. The change in energy is going to be that Rydberg constant multiplied by 1 over nf squared, or 1 over 6 squared, 36, minus 1 over 2 squared, 4. So doing that calculation should give you an energy, a change in energy of 4.842 times 10 to the negative 19th. I'm being kind of loose with sig figs here. Don't worry about sig figs. Technically, these are all exact numbers. I just chose 4 because, I mean, this is written in 4. I'm being loose with sig figs here. I can now take that energy and put it into the equation that relates energy and wavelength through E equals hc over lambda. I can take this first equation and rearrange it for lambda, or wavelength, by cross multiplying. So my wavelength is going to be equal to Planck's constant times the speed of light divided by the energy that we just calculated. And I see my units cancel, the joules and the seconds, and I see I'm left with something in meters. Wavelength is in meters. So doing that multiplication and division gives me an answer in meters, which I went ahead and just converted to nanometers. I didn't have to, but I went ahead and converted it to nanometers to show you that the answer that you get for this problem makes sense compared to the other wavelengths of energy that are calculated and seen with other particular transitions in the hydrogen atom. So you should be comfortable using this equation, second equation, along with the relationship that involves Planck's constant and the speed of light, to do calculations with regards to energy and wavelength with regards to the Bohr model of the atom.